we have to go back to Enceladus. I say this all the time, and that's because of all of the places in the solar system, Enceladus is the one where you've got liquid water that is actually being thrown off into space from these vents at the south pole of the moon of Saturn. Not only is there water going out, there are also hints of hydrogen gas. There are organic molecules in these plumes. And so if there is life on Enceladus, it's doing all the hard work of getting this material out into space. All we have to do is just taste it. But then how you actually sample these plumes changes depending on the kind of mission that you want to do. Do you want to go quick and dirty, cheap, fly through the plumes, go fast? Do you want to go slow with a more flagship mission that can actually go into orbit around Enceladus for a long time? Maybe even deploy a lander. It all depends on speed. What is the velocity that you need to be going so that when you actually collect these samples in the plumes, you don't destroy them? And this is interesting because at different speeds, different kinds of molecules start to break apart. Now, my guest today is Professor Mark Burchell, and he's the Emeritus Professor of Space Science at the University of Kent. And his work is to find out how fast you can smash into things and they still survive. And the answer is going to surprise you, from ice to metal to rock to organic molecules, to bacteria, to tardigrades, water bears. How fast can a water bear slam into a collector and still be able to survive? So we talk about just a range of amazing topics about what it would take for us to be able to extract samples from the plumes at Enceladus, maybe Europa. What about Io? Can we get some bits of volcano? What about material around the moon? What about tracking space junk? It's one of the most interesting and fascinating conversations that I've had in a long time. And I think if you're even mildly interested in the topics that I'm presenting, I think you're going to really enjoy this interview. All right, let's get into it. There's a whole bunch of things that I want to talk to you about flying through icy plumes and dust and all that kind of thing. But you launched tardigrades with a gun? Can you tell me about that?
Yes, well, the thing in space is you encounter things at high speed. So it's not like normal here on Earth where you drop something or a car drives down the road at what we think of as high speed. But in space, orbital mechanics are dictated by gravity between two objects. And so kilometers a second is a natural unit of speed. It might not sound a lot, kilometers a second, until you realize it's 36,000 kilometers an hour. And you crash your Ferrari on the motorway, freeway at those speeds, you end up with a vaporized fireball. Problem for us is if we collect dust at those speeds, what happens to it? And so we've got a gun which can fire at nice high speeds, equivalent to certainly some of them in space. And problem is, if you were at a icy ocean world, spraying ocean out into space, and you happen to spray out some microscopic life forms with it, which wouldn't be tardigrades because they're freshwater creatures, and we're talking brines, salt-rich things here. But imagine a similar creature. Hardy tardies they're called. So they can survive lots of stresses, and they're a model organism for testing. So we thought, okay, what would happen if they were being sprayed out into space at one of these plumes and a spacecraft flew by? What would you find? And so we published a paper now about 3-4 years ago where we put some in one end of the gun, we froze them, because they'll be frozen once they're ejected in these plumes. They freeze rapidly. Spacecraft flies by and sideswipes them. And so we reproduced those impact speeds and the shock pressures that they would experience. And we found that up to about a kilometer a second, they'll revive.
They're
above a
so
kilometer
tough.
a second, they don't revive. So that's unfortunate and sad.
Yeah.
And the student who did that, Alejandra Munoz Traspas, she got her master's thesis out of it. It was all very exciting. We published a paper to great acclaim, and people keep talking about it. But of course, we don't know if there's anything out there.
Yeah. Of course.
Those people from Israel are reputed to have launched some tardigrades at the moon a couple of years ago, and it crashed. And the question is, would they survive or not? And it depends on the impact speed of the crash and the structure inside the spacecraft. But at the speed they're going, they probably didn't survive.
Right. But it would have been greater than about a kilometer per second.
They were probably a couple of kilometers a second. But if they landed slowly and then just crashed at the end at a few hundred meters a second, the tardigrades would be fine.
Wow. All right. All right. So just keep that in mind, that tardigrades are as tough or tougher than we can possibly imagine. They really are like Mother Nature's perfect life form.
Yeah. And they can suspend themselves by ejecting all their water. So they go into this ton state, it's called, where they're effectively dehydrated and desiccated, lose 90% of their mass. And you can keep them for years like that. And then you revive them, add moisturizer, as it were, and revive them, and they're fine. So they are really hardy creatures.
Yeah. I think we're just fortunate that they're so small. Otherwise, we might have a problem. All right. So I want to talk about the actual paper that I reached out to you for, and I'm kind of obsessed with going back to Enceladus. I mean, obviously, all of the emphasis is on Mars. Let's search for water under the surface on Mars, but we're finding that these ocean worlds are becoming more and more interesting. There could be these vast oceans of liquid water that they've got dissolved hydrogen in them, that organic material, and with Enceladus, this stuff is being thrown off into space, which is such an amazing opportunity. So, what do you envision a sample, some kind of way to sample those plumes in situ, or even to bring some material back home?
The first thing you said is 30 years ago, NASA said, find the water. And it turns out the water isn't on Mars. People still keep going to Mars. The water is on those icy ocean worlds in the outer solar system. It's not even here on Earth. You might think, well, look out the window. If you're in California, you can look out and see the Pacific. There is more water on some of these icy ocean worlds than there is on Earth. So if you want to follow the water for life, you wouldn't even look on Earth in our solar system. You'd look in the outer solar system, but it's covered by ice, so you can't get to it, except as Enceladus goes around and round its parent planet, Saturn, there's tidal effects just stressing it, squeezing it, and effectively water gets squeezed out in plumes, a natural fountain. So all you've got to do is drink the water. And there's two ways of doing it. One is to fly by and sort of hold your hand out and try and get a cupful. And the other would be to land on the surface. And you might think, well, I can just dig at the ice. But the ice is so thick, we're talking kilometers thick ice. So you'd hold your cup out next to the bottom of the plume. Water goes up, ice goes up, and it falls back down like a fine snow. So you just sit there and you still get freshly emitted water, which is not quite coming directly from the interiors. It came up through vents, and it might have, in the vents being picked up, it might have had mechanisms to accelerate it. So you're not seeing maybe the direct connection that it came straight out the interior, but it should be material that is not contained in the water, but the salts and anything else in the salts. And the great thing is, we didn't know it was there. So back in the 1990s, when NASA built the Cassini spacecraft, it was going to go and fly an orbit around Saturn and do exciting things. They didn't know there were any plumes there. So there was no instrument on board to measure plumes. But there were lots of other instruments, great instruments. And so they were able to see the plumes by imaging them. And there's some dust detectors. And one of them detects micron-sized dust grains. These are grains 1/1,000,000th size of a meter or 1,000th the size of a millimeter. And it flew through high speed. You vaporize some of these materials, and they're able to see salt. Yep, so there's salt water in there. That's the first big. But then in future passes after the first one, they're able to see that there's also organic molecules in the material. There's short organic molecules and long organic molecules, low and high mass, in other words. And that's about it, because Cassini's now over. And for a spacecraft which didn't know what it was going to discover, it did brilliantly. People are still looking at the data and trying to understand it more and more. But if you could go back where instruments designed, you can fly past because you're in orbit around the parent planet, and that would give you a speed of maybe 5, 6, 7, 10 kilometers a second as you fly past. If you could go in orbit, you can get a much lower speed, several hundred meters a second. And then the collection, every time you go around in orbit, you will collect material. And so you can design instruments which can try and, if you have an orbiter, you can collect every time you go round and round and round. They're not necessarily circular orbits, because Saturn will perturb your circular orbit and it'll become more, you design an elliptical orbit probably. And there are mission concepts to do this. NASA always has plans. It's selecting the next mission, because space is great, but space is hard to get to. So you need someone to put up the money, and NASA can only afford the occasional mission to the outer solar system. But if you could do one, you've got the whole question of what type, the flyby or the orbiter, and how do you collect it? How much can you collect in each pass? What altitude? If you think of a plume, as you shoot stuff up, the big heavy stuff falls back first, only the fine light stuff gets to high altitude. So you go for high altitude, low altitude, how safe can you get? And then do you just want to collect it? And as you say, do what's called in situ science, where the instruments are all on board the spacecraft? Or do you want to do, which is everyone's worst nightmare, bring it back to Earth? Because if you bring it back to Earth, apart from making the mission more expensive and more complicated, because you have to take a motor on the spacecraft with propellant so that you can leave the Saturnian system and come back to Earth again. So that just takes up mass and leaves less mass for the science instruments. So the scientists at that stage go, I'd rather do science in situ, because the other problem with bringing it home is there's something called planetary protection, which says that's a potential site of biological interest. First of all, we don't want to contaminate it, but also we don't want to back contaminate the Earth. So you would find there would be severe precautions imposed on bringing something back from Enceladus, but even bringing stuff back from Mars, the proposed Mars sample return, which NASA is aiming for the end of the decade, although that does have financial constraints on that mission, so it might slip a few years. That also has severe planetary protection issues, and so they're working on the protocols now at NASA and agencies around the world to bring material back of potential biological interest, whereas when it came from the moon, it was just lumps of rocks. Everyone agrees the moon is inert. Bringing it back from Mars, that's a grey area. Bringing it back from Enceladus, where you're not talking rocks anymore, you're just talking little grain by grain, or little ice by little grain of ice. But do you really want to bring it back without having first known what it is? Do you want to seal it in containers and make sure it only gets opened in a sealed, inert environment where it can't possibly escape? I think both NASA, responsible scientists, and the public would all agree, let's be cautious on that last bit.
Yeah, I believe there's a few movies
yes.
have looked at what happens
David
if you do that.
Duchovny, things like that, yes.
Yeah, exactly. So I'm sort of envisioning a couple of possibilities. And you mentioned that this is maybe a priority in the most recent decadal survey. Astronomers, space scientists, planetary scientists, they said that a mission to Enceladus is one of their priorities. They would like to see that on the books. Now, who knows if this will actually get initiated and designed in this next run, but maybe it'll move higher up the chain next time. But I'm sort of imagining a few possible types of missions. You could do a flagship where you go to the Saturnian system, you stick around, go into orbit around Enceladus, spend a bunch of time orbiting Enceladus and gathering up all of those samples, kind of like Perseverance style. But I'm also imagining higher speed flybys where you just make one quick flyby through the system and then maybe a free return or a slight maneuver and drop back down into the inner solar system and return those samples back. And so I guess the work that you're doing is like, what are the constraints? How fast can we go and still get good samples either to test out on the spacecraft or to bring them back home to Earth? What are the parameters that you have identified?
Well, there's groups around the world all urgently working on this question. So there's now a scale emerging where people sort of knew, but are really focusing on the question that at a few hundred meters a second, an ice grain, a little grain of silicate rock, would just bounce off your collector. And if you design it carefully, it will bounce into the interior rather than bounce away from the spacecraft. So you can collect low-speed stuff. For us, low speed is several hundred meters a second. But after a few hundred meters a second, it will start sticking to a soft metal surface, indium or aluminium, soft aluminium. So you can start imagining at a few hundred, 500-600 meters a second, you actually have entire grains stuck now in your metal surface after your fly through, and you just got to scrape them off somehow or flow some liquid over the surface, water, to dissolve it and get it into the interior instruments. So there you would be getting intact grains at about convenient 500 meters a second. I say low speed, they would bounce off. So unless you angle your collector like a funnel, they might bounce away. So you've got to make sure they bounce into the interior of your collector. Then, as I say, about 500 meters a second, they will be sticking. But as you get about 800-900 meters a second, they start to fracture. They form craters in the target and break apart. And above 1 or 2 kilometers a second, you get shock effects where there's shock heating, and you'll find things start to melt and vaporize, and things really fragment. You don't find much. Instead of one grain, you find 1,000 fragments, for example. So for years, we specialized in measuring things like this, and the shock effect doesn't just break them apart, it will start heating. That's why they melt, and then you get the vaporization. So you worry what processing then occurs. If it was just a lump of silica grain, a lump of rock, you might think that's pretty straightforward. But if it was water-rich rock, you might find a selection bias. You keep the ones easily which didn't have any water in them, but the ones which had some water-rich content, they might find themselves vaporized and processed, and you don't find them so easily. So you bias your results. And if you think about organic materials, they're really susceptible to impact damage above 1 or 2 kilometers a second. And then, depending what instrument you put on board, you will find heavy selection biases because from the same instrument, suppose you could somehow connect up a mass spectrometer, which Cassini space mission did have. It had a form of mass spectrometer on board where you use the impact speed to actually vaporize the projectile and just measure what was in that vapor. And it was a very clever instrument designed by
that's really smart.
Called CDA Cosmic Dust Analyzer. And there, if you were at 2-3 kilometers a second, you got the major mass peaks out. You just break something apart into a few. It's like having your Lego bricks. You might get the roof off. Do you use Lego in California?
I'm in Canada, but yes.
Oh, so Canada. Sorry, my mistake.
Yeah. We of course.
Yeah. So you get maybe you pull the roof off the house. You get an intact wall out of your Lego model first of all. But then as you go up to 10, 15 kilometers a second, you start getting individual bricks. And then you've got to work out, okay, if I've got a few walls and a roof at low speed, I can probably work out what was going on. But then if I've got slightly higher speed, I'm just getting individual bricks. I've now got to work out how all those bricks went back together. And even worse, if you get above about 20, 25 kilometers a second, you're probably breaking even the bricks apart. So you've now got to think, how did all of that go together? And depending on your mission profile, you get a different impact speed. So which one is the best one from my type of instrument? And people who want intact grains would like it below a kilometer a second. People who said, well, my mission flyby is literally a flyby rather than an orbiter, they might say, therefore, we're going to be at that 4, 5, 6 kilometer a second regime. And so you've got to design your instrument knowing all the biases and think of all the things you might want to collect. And then you test them. And you go to, say, a gun like we have. Other people have electrostatic accelerators where you can take small grains, put a charge on them, just accelerate them. And they can get to very high speeds, but you can tune the speed then to what you want. And then you just do the experiment. You put your detector in, you dope your projectile, you dope the water ice, for example, with some organic material. Or what we've done at Kent over the years is we've put microbes in to see if microbes can survive. And that was we were one of the initiators of that sort of program of work. And it depends on the impact speed again. Above a kilometer a second, the survival rate falls down. But that's viable microbes. If you just had a plate of agar, this famous solution gel that bioscientists use in the lab to culture things on, if you just stuck that outside, stuff flies straight into it, bring it back on board, warm it up a little bit, put some oxygen over the surface to help some growth, you would see what grows. But above about a kilometer a second, the survival rate falls off rapidly. So you might get 1% surviving at a kilometer if it's a spore or if it's a microbe. But if you go to 2, 3, 4, 5 kilometers a second, you're getting 1 in 100,000 surviving. And above 5, 6 kilometers a second, probably none, because the numbers just don't work out anymore. So we did things like that. We looked to see what happens if you fired seeds. But seeds are actually very complicated things. Most seeds are actually quite large, and they've got structures in. And again, there's these thresholds. Once you get to around a kilometer a second, the seeds start tearing themselves apart during the impact, and they just then cease to germinate. But you still got big chunks of seeds until you get to 2, 3, 4 kilometers a second, where now the fragments are so small, you have difficulty recognizing what they were. And so we've done seeds, we've done microbes, we've done spores, we've mentioned tardigrades already. But the reality is, realistically, if you're designing an instrument for a place where nobody knows what's there and nobody has ever seen life before, so you're going to play it safe and you're going to say, let me assume that I've got some pre-biological compounds. some organic materials that don't necessarily mean life, they just mean chemistry has occurred. Chemistry is ubiquitous. Chemistry goes on everywhere. You have some energy and you have elements, you get chemistry. You add a few electrons in and you get the world we know around us. That's why chemists are so busy, because they're busy synthesizing everything you can think of. But if they can do it here on Earth, and if nature can do it here on Earth without life, then it's done it on Enceladus. So the safe thing is just to make the inventory of all the organic contents of that ocean. But if you play it safe, used to be the I Could Have Club. I could have won the Nobel Prize. If only it had occurred to me to leave the window open with my instrument to do something a bit more sophisticated. So someone has to see if they can persuade the mission to bet the ranch, even at the wilder edges of the idea spectrum, because otherwise you'd do an expensive mission which has to produce science. The safer science is to characterize all those pre-biological materials. But it would be nice if you had an instrument which could also just be sensitive to something alive, whatever it was.
Right. So it sounds like, here come all the compromises, which is if you want an inexpensive mission, then you're going to have to go fast, because it's going to be, you're not going to have the propellant on board to be able to go into some kind of insertion orbit around Enceladus. You're just going to blast through. And so do you think there's a sweet spot? I mean, to get you the vast majority of the science goals that an astrobiologist might want without having a giant school bus sized flagship doing the mission.
So that's where you start thinking, a cheap mission, can I do it under NASA's budget cap of, say, $800, $900 million? Or is it going to be $1 billion plus, in which case you get into the flagship mode? Could you get it down to $600 million? And the answer to these questions are where the compromises come in. There's an engineer sitting in the corner of every meeting going, can't do that. Can't do that. Well, I can do that, provided you take something else off. Yeah. And the engineers win every conversation because they're going to guarantee the mission works and comes in under the price cap, gets launched, reaches destination, and operates okay. But the scientists just then, you have to compromise. Which instruments? Camera. Fair enough. But then dust detector? I'd argue for a dust detector. Is it going to be optimized, however, for this type of dust or that type of dust? Is the mission profile going to include orbits of, say, Enceladus? And then someone will say, can we go to Ganymede as well? So can we, because this Ganymede's a nice, exciting body. Meanwhile, there's a whole group of people, by the way, who don't want to go to Saturn. They just want to go to Uranus. Do a close-up grand tour of Neptune or Uranus. Yep. You'll discover who knows what, because we haven't done a close-up grand tour of those systems yet. We've been past them, but having an orbiter around those planets and seeing what's there will itself be revelation. So you're also fighting off a group down the corridor who want to go somewhere else. So somewhere, science compromises, and it used to be said as a joke that in England that science isn't decided by the scientists, it's decided by the civil servant who gives you the money.
Mm-hmm.
And in the end, you've got to persuade NASA that money will be well spent.
Right. So let me ask you the question again. Do you think there's a sweet spot?
I would say yes, but then my sweet spot might not be yours. My sweet spot would be you can get there, but you can't come back. So you can get there, you can do a tour of Saturn's system, you can go into orbit around Enceladus, you can do some low-altitude passes, some high-altitude passes. Enceladus, those orbits will mean to be low speed, so you can collect lots of material without biasing it by damaging it during the collection. Then, yes, the rest of the mission can then boost itself away and go into orbit around Ganymede as well.
That's if it's Europa. I mean, now you've jumped to Jupiter.
Yes, that's Europa. My mind's jumping. Yes, if people want to go to Europa or Ganymede, they can have that argument.
Yeah.
But you can go around the rest of the Saturnian system.
Right.
People seem to be deciding right now, for example, to get back to Saturnian system, quite right, they don't want to go to Titan anymore. But a few years ago, they all wanted to go back to Titan. Now there's some counter arguments against Titan, and Ganymede seems to be jumping back into favor. So you say you restrict yourself to one planetary system, but you can visit several bodies, or you can go into orbit around Saturn first, and then finally go into an Enceladus orbit. But you will still compromise on how many instruments you carry. And some people just want to look at Saturn itself. I mean,
Right, but now you're recreating Cassini, and
I
that's
know.
a $10
So we've done
billion
Cassini.
mission. So, like I really want to work with you here. I've got a lot of budget, but we can't do another Cassini. I'm
Yeah.
sorry. But I
So
want to
you go to
get,
Enceladus because it's the thing about Enceladus. It's the one place where you know there are plumes from a water
yes.
world. Io, you'll know there are plumes from a volcanic world around Jupiter. But
Yeah.
Saturnian system, if you go there, you must go to Enceladus, I would say, because you know there are plumes. It's a fixed point you can anchor your mission design on. And then the only question is, do you leave the mission broad to visit other moons of Saturn? Or do you want to focus on Enceladus and go into orbit around Enceladus and say, do the low passes, the high passes? There's something called the Enceladus Orbi-Lander concept, which has an orbiter and a lander. So you try to get a lander on board as well to take it out there so it can land near the base of one of these plumes and collect material from the surface. So you've got two bites of the cherry, orbiter and lander. And meanwhile, you're taking up mass. So white papers get written, NASA gets lobbied, there are design exercises, you go through various phases of study, and you increment your way forward, and NASA says no, but come back in a year or two time having answered this question, this question, and this question. And each time you get a bit closer.
All right. Mark, it's just us. Nobody from NASA is listening. Nobody from ESA is listening. I want to know if there are either the precursor molecules for life in the plumes of Enceladus, or even if there are biological material, bacteria, maybe even tardigrades. I want to leave a little cushion on the high end of the complexity. Seeds, I don't mind smashing a couple of seeds. I want those samples, and I would either like to analyze them in situ, or I'd like to bring them home. What's that mission, do you think?
I would go for the orbiter around Enceladus.
Yeah.
You will find that the grains we're talking about are probably only going to be a few microns in size. A 10, 20 micron grain would be a boulder. So you're not really going to find life. The tardigrades I mentioned, by the way, are typically 100 microns across. So it'd be very hard to find one of those lofted to high altitude. So you might find bits and pieces. You might find the detritus. So one of the things we did a few years ago, for example, was we just took fossils. If you go down to the beach, you will find fossilized, we're not talking dinosaur bone fossils, but if you're looking fresh water at the beach, you can find all sorts of little creatures and animals and their shells. So we looked at diatoms, which is freshwater shell-like structures, and they can be broken apart, and they have characteristic structures. So collecting material, which collects material, which isn't biased, and can put it in front of a microscope, that alone is mind-blowing to see what structures look like at that sort of scale. And then, yes, then do the elemental composition, then do the mass spectroscopy where you're not just looking at is it carbon, oxygen, nitrogen rich, and what chemistry is it undergoing, but can you see how it's bonded? If you are going to have intact polycyclic aromatic hydrocarbons, that would be great. So you need an instrument to maybe detect those. But if they're going to break apart a mass spectrometer, we'll see characteristic series of peaks. So very high resolution mass spectrometer, plus some collection medium which can also collect the larger fragments and put them in front of a microscope. And then your lander can have something similar because it'll be raining out the sky. The stuff that goes up a little bit and falls straight back, that will land on your lander. And
Whoa,
so
I didn't ask for a lander, but okay. If you want to add a lander to the pile, we'll see if there's room in the budget for this.
And it will be continual on the lander because it will be a continual fountain.
Yeah.
You will get more from a lander than you will in your orbiter. But of course, a lander takes complexity. It does take mass, and you've got to think that only a small fraction of lander is actually the instrument, and a small fraction of the orbiter was the instrument and the lander. So putting a lander on is one of those.
That was a bold proposal. I'm surprised you included it in there, but I'm going to hold you to it. You're going to need a second RTG to power the lander for long enough to be able to collect samples. But I'll take it.
Know. And then you've got to think of how do we get it all under the price cap that NASA will impose on us. So we've got to try and cut corners, not scientifically, and the engineers want to cut engineering corners, but make the instruments multi-purpose. Make them as simple but robust as possible so that they will survive and give you answers.
But But in general, your preference is go to Enceladus, stay at Enceladus, do your
Yes.
analysis in situ. Don't try to bring samples home. It's a sort of a
Not on
different
the
mission.
next mission.
Yeah.
Return would be
Okay.
later.
Yep.
By the time you've got your first mission to Enceladus, we're talking the 2030s. By then, not only will you have whatever Enceladus tells you is there, but you will also have all the experience of Mars sample return about how to handle samples, bring them back to Earth with planetary protection protocols. And we will have a much better idea of both what we're targeting at Enceladus, because we'll have done another mission there, and how to bring it home. Now, of course, at this stage, I say all the other people who want to go to Jupiter again, or want to go to Uranus and Neptune, they're all lobbying. They're all sitting out there as well. Because they'll say, why go multiple places? Well, is it multiple times to one place? But then that's what we've done at Mars. And that's how we know so much about Mars, because people kept visiting Mars again. And if you gave up after the first rover mission, so we've had a rover, you wouldn't have learned much. So you go and make repeated missions. And that's where the real scientific yield comes from to me. And then, yes, well, I'm going to pat my not quite full head of hair anymore. And it's not quite the color it was. Because the other thing about these missions is you're talking a decade of preparation, a decade-long mission, and a decade of analysis. Cassini really got the green light in the early 1990s. This is to Saturn. But it was been proposed throughout the 80s, green light in the early 90s, launched. What was Cassini? Was that
2003?
97?
Oh, 97, I think.
Yeah.
No, wait, maybe I'm thinking of Galileo. But it was a 10-year trip to get out to Saturn.
It's a multi-year trip.
2003, 2013, I think.
It was Cassini was at Saturn. I don't know,
Yeah, maybe right. Arrived in 2003,
yeah.
So it launched late 90s. Yeah,
7. So say 6-year flight, but then you're going to have a 10, 15-year mission if everything goes well, and then you can analyze the data afterwards. So you get one shot in your lifetime as a scientist. And what you would really do, of course, is you would start your PhD and your postdoc positions on one mission. You move to your faculty position, your big stage of your career in your 30s, 40s on a second mission, and then you finish off the end of your career like I am now, helping design future missions, which I will never see.
Well, unless you work with, like, say, the Voyagers or something, some of these spacecraft, you start as a grad student and you're retiring and you're still working on that mission. Some of them are amazingly long-lived. So, we've talked about Enceladus and all the possibilities. I would like to sort of consider some of the other places which are somewhat similar environments. What about Io? But now you've got volcanoes blasting chunks of rock into space.
So there are people, and we're part of a group, a study looking to go to Io. So HRBS, why not just go there? Why also go to Io? So you can call it fire and ice. And it's totally different chemistry now. We're looking at sulfur-driven eruptions. We're looking at grains which have come from the interior of a molten body. So now you've got more robust materials. And again, that makes collection easier because as your flyby speed is critical, but the materials are a narrower range of material and they're not susceptible to damage as, for example, you might find with organic materials. And it's a bit closer. And now you can consider a flyby because there's no planetary protection issues either. So the combination of you're not quite so worried about the speed, you don't have to get it below a kilometer a second, and you're not worried about the cost of planetary protection, means you can really envisage a flyby at Io through that nice fountain of material that's shooting up. And you don't even really need to target which volcano, because there seem to be several hundred active sites. There's certainly about 250 hot spots on Io. Whether they're all volcanically active on any given day is an interesting question. But the thing about Enceladus is you've got a continual plume, it seems, but same with Io, you've got a continual plume. You don't worry you're going to turn up and discover the plumes all stopped last week. So you've got a mission you can guarantee a sample return from, and you just need to think the missions around now in that system should be sending back data with the Juno cam, I think it's called, which will allow you to nicely image, to target where these things are, to try and profile the heights and widths of these. The modeling will tell you what the spatial density of material is, so you can predict how much you get on a single fly past. or do you really have to try go into orbit around Jupiter and fly several times past Io until you've got enough material statistically, and then you can come home again? And so you can now really seriously think about a different type of mission with a different profile because it's got different constraints.
Rocks can handle the impacts a lot better than
especially
squishy
rocks that
organic
probably
molecules.
just come out of a volcano.
Yeah.
Now, they may actually be fragile because a lot of volcanic dust is fragile. So that is an issue. If you remember, is it 2011 with the Icelandic volcanic eruption, which may not have affected people on the Pacific coast of Canada much, but certainly closed down all air travel in Europe because I got stuck in Germany. And what can you do? You just go to a hotel with a credit card for several days.
There's a volcano.
Yes.
But
some of that volcanic ash, we did experiments with it afterwards, is actually very fragile. Even though it's come from the interior of a hot volcano, it condenses into very flake-like materials. So some of that won't survive intact, the impact. It will just break apart. So its structure will be there in a sense of its composition, but you won't quite know what its shape would look like before it hit your spacecraft because it will just crumple on impact. So you will lose some details about how porous it was, how distributed the material was, how flake-like it was. And you just have an impact site if it's a high-speed impact, but all the materials shoved into your collector at that impact point.
I can just imagine, like, it's a volcano out and people are worried about their travel, and you're like, I got to get some samples to put them in the gun to find out what's going to happen.
Unfortunately, we never published that paper, but yes, people sent us volcanic samples of ash that had settled near volcanoes. And it was actually a big project because it was really about ingesting materials into jet turbine engines and how much damage they would cause, because that helps set the volcano is still erupting in Iceland even in the last few months. So do you close down all air travel again? How much dust can you tolerate before it gets to be an issue for a jet engine is actually a serious question here on Earth. So there is interest in that sort of research. And jet turbines, the rotor blades move very fast. And so you can suck all this in at high speed. It gets heated up. What damage does it do to your rotor blades? And the rest of the interior of the engine is a big question. So, that is a question for Earth's aerospace engineers. For the aerospace engineers at Io, it's how can we collect that dust and try and characterize it so that we know before impact, not just its composition, but its structure, its appearance, what it looked like. And that tells us the material that's spewing out into the space around Io.
Now, there is a bit of an analogy, though, with the moon, as we're seeing more and more spacecraft going back to the moon, and as large spacecraft, like, say, Starship, attempt to land on the moon, they're going to kick up pretty big dust plumes. And there's a lot of people, I think about, say, Phil Metzger in Florida, working on what is the contamination of the lunar environment? What kind of risks are we looking at for spacecraft to attempt to land on the surface of the moon? But I wonder if all of that dust that's getting kicked up, all that regolith, is also a research opportunity that you could fly through it, collect samples, learn about the regolith at different parts of the moon.
Well, by strange coincidence, I sit in the European Space Agency Working Group, which is considering the Gateway, the new lunar space station that's going to go into orbit around the moon at the end of the decade. So NASA has this two-prong approach to getting people back on the moon. And I say people deliberately because it will include the first women on the lunar surface. That's the Artemis. But there'll also be a Gateway, which will be a station that's inhabited occasionally around them, not continually. And there are two locations there where you can put dust detectors. One is down on the surface, and there you can stick the dust up and bring it back anyway. But also there's a little influx of micrometeoroids all the time that will just hit the surface, and you might want to measure that on the surface. Or if you're in orbit, you've got to think, I can put a dust collector there, but where will the dust come from? And one of the things we've been considering is if things hit the moon, they will throw up clouds of this ejecta. And how much will we really find at high altitude? And the answer is very, very little at the altitudes of 1,000 kilometers or so where the space station is going to be. So that's unfortunate for us. We'll still be able to see interplanetary dust. We'll still be able to see interstellar dust that comes into the inner solar system. And there's a little window of opportunity where that normally gets deflected by the solar wind. But the solar cycle is changing in the early 2030s. So we'll get more of that dust in the inner solar system than we do in a normal year in the early 2030s. So there's interstellar dust, interplanetary dust, there's cometary dust streams. And then another source is whenever someone goes down to the lunar surface and they come back up on their spacecraft, there'll be dust stuck to the surface of the ascending module. And it might creep across and start sticking to the surface of the gateway as well. So it won't come directly as an ejector, but it might be lofted on board as a passenger on the ascending module, which when it goes thunk and docks, it can shake stuff off, which can transfer over, or electrostatics sticking can allow dust particles to jump across surfaces. So we might find there's contaminants which end up on the outside of the gateway from the lunar surface via that route rather than via direct ejection.
Wow, yeah, that hadn't even occurred to me that you could still, even though the lunar gateway is so far away from the moon, you could still end up with that dust contaminating the exterior, and who knows, maybe it finds its way into the interior if they're doing spacewalks and things like that.
Well, if they do any lunar walks, they will get dust on their spacesuits. They'll go back inside. The dust will now be the interior. And there are several. One issue is health. If you ingest this dust, if it is fine flakes, it's not good to be ingesting it or breathing in through your nasal passage, but also into your lungs. Very fine fragments of sharp-edged material is not a good idea. But also, there's enough of it on those spacesuits that people were extracting space dust, lunar dust, from bits of the spacesuits, which they were cutting up and getting dust from. So it has happened already, and it will happen when astronauts go out on the lunar surface. Every spacewalk, when they go back inside, they will it's like your house. You trample stuff in. It's from outside. It's why you have carpets or whatever. Why you insist people put on slippers. But here they're going to be taking their coats off, their fake spacesuits, and the dust will just fall off that into the interior.
One of the most fascinating discoveries made in the last couple of years was the presence of interstellar objects in the solar system. We had Oumuamua, which was the first one that was found, and then Borisov, which came through like a couple of years later. We know that they're leaving trails behind them, especially in the case of Borisov as it got close to the sun. But these are not normal comets. These things are coming in at potentially tens of kilometers per second as they're passing through the solar system. They're on interstellar trajectories. They're leaving again. But it would be absolutely incredible to be able to pull a sample from an object that was formed in another star system. Considering the sort of velocities involved, what do sample return, or even just in situ sample analysis, how do you think about that?
Well, it's been done, not on those objects, but on Halley's Comet. Back in 1986, when it came through the inner solar system, it was a planned event, because that's why Halley's famous. He wasn't the first to observe it, but he noticed the periodicity and realized you could predict it coming back. But spacecraft were launched. There was a fleet of several of them. And it was the European Space Agency's probably first great space science mission away from the Earth. And, for example, and the Russians had some. And they flew by. And they did it at high speed, up to about 70 kilometers a second. So that's already been done, high-speed collection. And some of these impact ionization dust detectors, where the impact is so violent, it vaporizes the small projectile. These are submicron particles. But then your mass spectrometer just accelerates these using electric fields and measures them. It's a beautiful concept that I mentioned earlier, but it's been done. So the issue is, when is one of these going to come? So you don't know. Therefore, are you really going to spend a lot of money building a space mission which will just sit there waiting? Or if you do what the European Space Agency is doing with a Comet Interceptor mission, which should be launched at the end of this decade, if I've got my dates right. And I don't think they've even picked the comet target yet, but they're just going to fly past a comet with a lot of instruments on board. And they're going to see which comets are particularly active around about the time they're ready to launch and go to one. And so I suspect that in their minds, they mean a really active comet. And there are different types of comets where they originate in the solar system. Is it a fresh one? Is it one that's known? But they really want a fresh one. And whether you persuade them to change their minds if there happens to be, by coincidence, an interstellar object coming through at the right time, that would be a fascinating question. But, as I say, it's been done at Halley's Comet at that high speed. The European Space Agency plans Comet Interceptor, and that would be a high-speed past flyby of a comet again. But you don't know when there's going to be the next big interstellar object coming through, because by definition, you haven't seen them coming.
But hopefully, Vera Rubin, we're going to see first light from Vera Rubin next year. We should have 5 years of imaging the sky. So who knows? I like our chances if they're
Yeah,
willing
well,
to. I know do you leave that spacecraft just loitering, waiting at L2, or do you actually pick a target and go?
yeah. So I suspect several things that happen. First is once you find the first example of something, you now know how to look at it. And over the next few years, you find more, which were always there, flying through, but you never saw them because you weren't looking the right way. So there will be more discoveries. It's just my view. Because once you know how to do it, you know how to do it. But then the question is just how frequent are they of that size? And yes, all those scientists who helped build that space mission, that Comet Interceptor, they want to go and do some science. They want to go and look at comets. So the pressure, they will launch and they will go straight out and find something. And these are expensive missions again. So to leave one loitering somewhere on the off chance that somewhere within a window you will have something come through on a trajectory which gives you an intercept course, because it would be disaster, of course, if it was not going to be something we could reach with a particular mission class. So a mission class determines cost, and cost determines how much propellant and how big you are and things like that. So that would be a disaster. So again, you hedge your bets. You go to a comet. Comet Interceptor will fly past a comet on schedule. And
or an interstellar object if one is found. But I guess I just wonder, do the speeds of, say, the long period comets coming into the solar system for the first time, are they roughly similar to what we saw with Halley's Comet and what we would see with an interstellar object?
Yeah. The particular mission scenarios that for Halley's Comet, they were high encounter speeds, so they will be typical of the high encounter speed. NASA visited a comet in 2004 that was Cometville 2, and I worked on that mission. Don Brownie was the leader from the University of Washington, and that, by optimizing the encounter speed, was 6 kilometers a second, a much lower speed, and cometary dust was collected and brought back to Earth successfully from that mission. And it's been analyzed, and it's still being analyzed even today, even though the mission returned in 2006. People still analyze those dust samples, as some of them were kept untouched, waiting 20 years deliberately for better experimental techniques. Because you only do these missions once in a career, basically. So NASA has done it and collected samples at low speed and brought them back. As I say, the Europeans and separately the Russians did fly by Halley's Comet back in 86. So a nice pre-programmed mission like that would be great. And Comet Interceptor will fly past something come the end of the decade. Can't tell you which comet, I don't think.
Right. But you'd like to keep that velocity below, say, 6 kilometers per second.
If I wanted intact samples, which I was going to bring back, I would want it low speed. If it's just a flyby, then you just accept that it's a high-speed encounter. You're going to do a different type of science. You're going to vaporize the materials to take advantage of it. Just measure the mass spectra you get out of it.
The last place that I'd like to talk to you about is the potential of an interstellar mission. And I don't mean flying to another star, but there's a few missions that are being proposed now to fly out beyond, say, the distance that the Voyagers are at, where you're truly in the interstellar medium. Hopefully now you're seeing more interstellar material than cosmic dust that came from the solar system. How do you think about a mission like that?
The cheap ones are to wait for the dust to come to you, and you just do it in the inner solar system and wait for that dust to arrive. And I'd say that's why the early 2030s are so interesting, because the solar cycle means that the deviation, the solar wind pressure which deviates particles away from the inner solar system, especially the small ones, that will be vanishing for a little while. So a mission there just left in the inner solar system for that dust becomes a lot more viable. But if you go out, the question is, are you going to go out to visit something? Or are you just going to go there to do a whole range of measurements, not just about dust, but about the interstellar medium again, to find out where the boundary is from the solar system to the outside, how variable it is, to look at the radiation, to look at anything you can think of, magnetic fields, were instruments which were not designed in the 1970s, because that's when Voyager was built. Both of them, they're great things. They lasted 50 years. But these exceeded their lifetimes, planned lifetimes, by decades, and they're brilliant. If you did it again now, it's just worth doing because you've got 50 years newer technology. And yes, you just persuade someone that we might not be rendezvousing with a particular body out there, but you just want to go back and learn about interstellar science and the interstellar medium in interstellar space itself. And there are, I say enthusiasts, there are lobbyists who want to do that, but you lobby against every other space mission because you're talking a once in a decade mission, and you have to persuade ESA or NASA to do it. And
Right.
take a deep breath at that stage.
Yeah. Where do you want to go? We want to go nowhere. It's hard to when there's people saying we'd like to go to Enceladus, please, where there could be evidence of life. Yeah, I can see it's a tough conversation.
And then there are lots of science questions you can ask, though, about how the interstellar medium informs the local space, how different the two are, what's the dust like out there versus the dust in the inner solar system, how processed does it get? So there's great science which goes back to things like the formation of the protosolar nebula. So there's big science questions that you can ask, and how much material is coming out from here back out there. So we are ejecting material back into interstellar space from our solar system. So how much do we enrich that medium? If you could really do measurements which would answer some of these questions, you would be addressing profound issues of not just star formation, but planet formation. But you're fighting off every other scientist, every other planetary scientist and astronomer. And the astronomers will tell you just build a bigger telescope.
Right, but although astronomers are depending on many of their observations on a baseline assumptions of how much dust is out there in between their objects that they're seeing, so I'm sure they would
and
appreciate.
And that it's all silica grains of a certain size.
Yeah. Mark, what are you obsessed with right now?
What I'm obsessed right now is, oddly enough, we've mentioned Enceladus and the plumes. We mentioned Io and its plumes, so it's fire and ice. But also there's a major non-scientific, but it's an engineering issue, which is debris in Earth orbit. And the more spacecraft that go up, the more satellites, those constellations where people are talking 1,000 satellites in a constellation, they shed debris. And at the end of their life, they are junk, but also small impacts on them can knock off paint flakes. If one of them has a catastrophic disruption, it blows up, and that happens occasionally at satellites, malfunction of some sort. It will shower lots of debris out there. So the amount of debris is monitored not eagerly, but the morbid fascination by NASA and ESA, who see it going up and up and up. Their protocols for how to minimize it are getting tighter and tighter. You have to deorbit old satellites. It used to be at 25 years. Now it's saying, make it 5 years to get rid of them, because there's so many satellites going up. To wait 25 years out the end of life, that period is just too long. And something could happen to one of those satellites. It could explode. And of course, occasionally people do deliberately explode satellites in testing of weapons, whatever. But that is now increasingly seen as irresponsible. But this could limit working access to low Earth orbit for satellite constellations. International Space Station does orbital maneuvers to avoid impacts several times a year now. The various satellite systems that are up there that are providing all those kinds of communications facilities we have on Earth, they do them on, as far as I can see, on almost daily basis. So that is what obsesses me right now, is measuring how much of that debris is there and getting dust detectors in space, because big ones you can see with radar from the ground. Millimeter particles you can't really see with radar from the ground, even reasonable low Earth orbits. And millimeter size will punch through most instruments on most spacecraft. They can cause damage if they hit the main body of the spacecraft, which will mean it's inoperable, and they might start generating a bit more debris. If you reach a centimeter size, your whole satellite would go up. And then you get something called the Kessler syndrome after Don Kessler, who predicted many years ago that if you get a multiplication event where one goes in and the spacecraft explodes and you've got 10,000 coming out, if one of those then goes, you get a chain reaction, and then you could lose low Earth orbit. And so that's a worrying prospect. And so space agencies have teams and committees now thinking about some how to mitigate it by getting rid of spacecraft at the end of their life very quickly. Others are trying to make sure that the spacecraft themselves do not shed materials accidentally. And what I'm interested in is just measuring it to see how much is up there in that critical size regime, where people aren't measuring it very well at the moment. There's a few people trying to measure it, and European Space Agency, for example, has proposals where it wants to build large area detectors to try and measure this flux. So it's something that's obsessing some of us at the moment, that it's those dull science fiction nightmares, the ones where we can't put spacecraft in low Earth orbit anymore because something damages them too quickly. That would be rather an unfortunate legacy to leave our children.
Yeah, yeah. It's a different kind of, I don't know, orbital debris than some exciting samples from Enceladus. You're
Yeah,
just
it's
trying to
not
find out how
exciting
much
space
tiny
samples.
chunks of metal you're
Yeah,
getting impacting your spacecraft.
but it is unfortunate aerospace engineering problem, and it happens to use a lot of the same techniques because we're talking about high-speed collisions.
Yeah.
So here we want to characterize them, separate out the interplanetary dust from the debris so that we know there's always some interplanetary dust, but we want to look at the debris population, separate it out, measure its orbits, its size distribution, and see is it increasing. And this is a controversial question, and I'm afraid it does obsess some of us.
Is there a mission in the books? I sort of imagine some heavily armored space debris collector that is just trying to measure just how many impacts are crashing into it on
Well,
an
there's several types of
ongoing
missions.
basis.
One is to go and rescue old satellites and get rid of them.
Right.
So go and grapple with them, harpoon them, whatever, give them a boost, and put them into a decaying orbit and just get them out of the way so that you minimize the risk that one of them just starts shedding material or accidentally, so you forget where they are and it can hit something. So you don't want that to happen. So, and they might go out of control and they might hit something. So if you can get rid of them, and it should be the spacecraft operator's duty to get rid of it. Yes, it should be. But a 25-year window at the end of its life where they could get rid of it, that means you can see there's problems there. So making that window short is what NASA's doing. But missions to actually just get rid of one satellite a year, space agencies are seriously launching those and testing the technologies to do it. You've got to be able to dock, but you don't want to destroy it and accidentally create the debris. You want to dock safely, even if it hasn't got a docking ring, and then push it away into its new orbit. It's the type of thing I'm talking about. You don't need a heavy or armored space vehicle. You just need one with a large area. Because the large area means that you collect lots of little impacts and the rarer big impact. We want to know how rare those big impacts are and how frequently how rare they are. So that's the next design, which ESA has a proposal out for at the moment, where it's calling for people to work on that. And so we're part of a team of European industry which made a bid to ESA to design and build that for them, in fact, and we're waiting to see what they say. So ESA will be doing one of those, looking at that size range, which is too small to see by radar, which isn't measured properly by existing and previous missions, but which turns out to cause serious damage to space vehicles, and just at the upper end of that size regime, at the centimeter scale, can actually destroy small spacecraft.
I'm kind of imagining some sort of unfolding origami that creates this giant surface area, collects a bunch of stuff, and then at the end of its run, it folds itself back up into a small thing to be able to return to Earth. I wonder.
Think of an umbrella.
Yeah.
I mean, that's what an umbrella is. Oh, it's a long umbrella on a stick, but you just unfold it and you get a big surface area to keep you dry. In this case, you get a big surface area, and it's almost exactly what's being described. Something with spines which go out, a thin film stretched between them, little acoustic sensors to detect the impacts on these segments of that umbrella, space umbrella, whatever you want to call it. And so you have these, this beautiful unfolding if it goes well. But then people have been trying things like that with solar cells anyway. So the technology actually exists. You just got to marry the solar cell technology with dust impact sensors on it, get it built and launched, hope it works. The last dust detector I did work on with NASA stopped working after 3 weeks. It was supposed to operate for 2 years, but it had a comms issue. That was very embarrassing. It was called the SDS, Space Dust System. But so things can go wrong in space. But ESA wants to try. NASA, I think, is mandated to try again, although I'm not sure of their current proposal status. So there will be such an instrument. It will be very dull. It will be one of those missions that has to be done and will be vital to know and monitor. And consequences will arise if it looks like it's getting worse up there, because everyone's going to have to tighten their game.
That's interesting. And so it would just, by being this unfolding umbrella with acoustic sensors, it would know every time a piece of debris passed through one of its panels,
yes.
And you would know roughly the size and then I guess it would last as long as it's able to maintain its orbit and isn't torn to shreds, which you hope will take a much longer time. That's really interesting. I've never heard of that mission. I really like the concept.
Well, at the moment, it's a concept. So if things go well, ESA then pays for a proper design study of what we'd be doing. If we can demonstrate that it gets to the right stage of technology preparation, they then go. This is how European Space Agency work. They then go back to the ministers who vote the money, and at the ministerial meeting, they say space situational awareness. It's vital. Some of that means, by the way, solar flares coming from the sun and knocking stuff out. And so countries are quietly preparing for that and hardening up all their hardware in space and on the ground. But it also means damage to satellites from particulates. And so at that stage, if we've shown, or whoever gets the contract shows that it works, the ministers have to vote and put their money, and whichever countries vote yes, if they do vote yes, they get to build it. And their scientists and engineers get to work on it.
It's fascinating work. Mark, thank you so much for taking the time to chat with me today. I learned a ton with this conversation, and good luck. I really look forward to those first samples being analyzed at Enceladus.
Yes, that would be great.
Yeah, in both of our lifetimes.
Yes.
That would be great.
But
all right, take care.
Fantastic. So thank you for this conversation.
I hope you enjoyed this conversation with Professor Mark Burchell. I found it just absolutely riveting the entire time, and I just hope you did too. Now, I'm going to talk some more about my thoughts on this interview, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Antonio Lofilara, David Giltonen, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jordan Young, Josh Schultz, Mark Anstis, Paul Rohrbach, Stephen Krasaki, Stephen Filer-Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I mean, we say that we want to learn more about Enceladus. And in fact, planetary scientists in the United States set as their next goal for the decadal survey to send a orbiter and lander to Enceladus. So this is beyond, wouldn't it be great if we could get some samples from Enceladus, to, all right, this is now a priority by the scientific community to start developing the hardware that can actually pull this mission off. And yet I'm seeing lots of really interesting proposals. Well, maybe there's ways that we can do this kind of quick and dirty. Maybe we just go fast and we just blast through the plumes, collect some samples, maybe study them locally, maybe bring them back to Earth. And I think we're in this interesting time with sort of, on the one hand, you've got all this miniaturization and new ideas about propulsion systems. And then on the other hand, you've got a complete change in the kinds of places that we want to explore. You're not looking at the surface of Mars where you send a rover and it crawls around and digs at rocks. You're trying to imagine how you would collect samples through plumes of water ice that's being thrown off into space. And it's a totally different both mission concept as well as how you're going to try and collect these samples. And yet, I think the viability of life to be in places like Enceladus, Europa, Triton, these other worlds, has sort of surprised the astrobiology community. All of their eyes were focused on Mars, and now suddenly, no, let's figure out a way. And of all of the worlds in the solar system, Enceladus is the one that is just obviously begging for us to send a mission. So let's send that mission. All right, I've got a bunch of other interviews about Enceladus and Europa and ice worlds on the channel, so check one of those out. We'll see you next time.